Good morning. Today we will study the same static fluids, lecture number 5. We have four questions. The first question and density, pressure in a fluid. And the second question, fluid flow. And the third question, work mechanical energy in fluids, Bernoulli's equation. And final question, and fluid viscosity and resistance. Today, and we uh, will study and the physical term density and pressure, the different pressure, and conclusion on the formula Bernoulli's equations definition and fluid flow, study fluid flow, and fluid viscosity and resistance. We start and the first question, density, pressure in a fluid. We know an important property and density. What is this density? Density and important property of substance and the ratio of its mass to its volume, which is called density. The formula of the density, rho equal of the ratio mass divided by volume. In here, this is definition of the density. The rho and here Greek letter, and usually they usually used to denote density. The unit of system international unit, and of the density, kilogram divided by cube meter. Of the different chemical element we will use and rho, and for different element, different value of the chemical element, And here, this is figure show you and different chemical elements, solid, liquid, and gas. In here, maybe for example, and solid and osmium, coal, lead, copper, iron, etc. And here, this is chemical element following solid, and the mercury, seawater, water, and gasoline, ethanol, and liquid following chemical element, liquid, and gas, air, steam, helium, and hydrogen. And this is a diagram show different chemical element for a different chemical element following density. And here, this is value of the ethanol, value of the density, and gasoline, and air, and helium, and hydrogen gas, and etc. We know, and the ratio of the density of a substance to the water is called specific gravity of the substance. For example, the specific gravity of aluminium 2.7, meaning that a volume of aluminium has 2.7 times the mass of an equal volume of water. The specific gravities of objects that are thin and the water range from 1 to about 22.5 for the densest element osmium. Most solids and liquids expand only slightly when heated and contract slightly when subject to an increase in external pressure. Since these change in volume are relatively small, we often treat the densities of solid and liquid as approximately independent of temperature and pressure. Okay, when a body is submerged in a fluid such as the fluid exerts and force perpendicular to the surface of the body. Each point on the surface. This force per unit area. A, this is area, the notate area. This is force per unit area, they called pressure. We saw in here, this is definition pressure. Pressure, the unit of the system international unit of pressure. And here of the formula Newton per square meter, which is called Pascal. 1 Pascal equal 1 Newton divided by square meter in here. But on the task we we had and 1 atmosphere. 1 atmosphere equal 101.32 kilopascal. And here this is kilopascal to replace the pascal, and 101.32 multiplied by 10 power 3 pascal. Okay, and here we'll take container consistent to one and piston, small piston, and the second large piston. And here the resultant is the pressure that the height is greater than the surface of the liquid is amount rho GH holds for a liquid than any container independent of shape of the container in here. And the pressure is the same at all points at the same depth. If we increase the pressure by pressing maybe down to on the top surface with the piston, the increase in the pressure the sum throughout the liquid. This is known as a Pascal is the principle. Pascal is the principle named after Blaise Pascal. In here, we take action on the small piston. In here, this is area, the small piston area 1. In the large piston have and the area 2. And maybe we take or action on the small piston, and this is system put on the action on the large piston too. And formula of the second force and equal the first of the ratio, the first force divided by area multiplied by the second area. The first area equal divided by E multiplied by the second area 2. We now, and here this is Pascal and the principle, and Pascal is the principle, and pressure applied to enclosed liquid, and the transmit a dimension to every point in the fluid and to walls on the container is the Pascal and the principle in here. And here the definition of the Pascal is the principle. The second continuity equation we now and we take and Friedrich in here. This is show fluid flowing in a tube of varying cross-sectional area. The shading on the left indicates the volume of fluid of flow. And here, maybe we take in here this fluid flow and in a tube on a varying cross-sectional area. If the speed of the fluid at this point is V1, this is velocity, the first velocity at the cross-sectional area A1, and the volume flowing in the tube in the time delta t, and delta V equal the first area multiplied by the first velocity and multiply by and in the time delta t. We now and then maybe and in here the since we assume the fluid to be incompressible and equal volume of the fluid fluid mass flow out in the tube at the point 2 and indicates the shading on the right. If the speed on the of the fluid at the point V2 in the cross section in here, this is the A2 volume delta V equal the second area multiplied by second velocity at the point 2 and multiplied by in the time and delta T. And we have the first volume equal the second volume and fluid flow, the quantity A2 is called volume flow rate. The dimensional and flow rate in here, the of volume per time, the steady flow in compressible fluid, the volume flow in here is the flow rate is the same at the point in the fluid. And this is continuity equation. Continuity equation E and equals the constant continuity equation. And the third equation, work mechanical energy in the fluid, Bernoulli's equation. We now, and here this is, we have tube with different area, But in the first part on the tube and the height and on the earth and Y1, the second part on the tube and on the earth and height and the second Y2. Even now and here, this is tube with different area, and here this is area, large area, and here this is small area. And here this is direction, shows the direction and fluid flow, and velocity show a direction of fluid flow. And here this is direction fluid flow, and the second direction, the second velocity. But and the small region in here, this is smaller region in here, from 1 to 1 strich, and here this is region, the second region from 2.2 to strich. And here this is pressure, I'm sorry, and here action, force action on the fluid flow and on the center, and here this is direction of the second force, and the small displacement, the small distance, and here this is distance delta x2. Bernoulli's equation, we know the Bernoulli's equation related the pressure, elevation and speed of compressible fluid in the steady flow. It follows from Newton's law. It most usually derived by applying the work energy theorem to segment of the fluid. We applied the Newton's law, and mostly derived by applying work energy theorem in here. Work energy theorem, we applied only segment of the fluid. Is a change potential energy, delta U, and here mg, delta mg y2 and minus delta mg y1, and here this is delta m. We replace, and we know formula of the density, delta m equal rho delta v, because in here this is volume and this is volume is the different, and we now change potential energy equal rho delta v, rho this is density of the fluid, and delta v, g is gravitational of the constant, and change coordinate delta y, and replace the height. As the change in the kinetic energy, we know formula of the kinetic energy mv squared divided by 2, but in here and the changing in kinetic energy because energy of the large area and the small area is different, changing kinetic energy in here, but delta m are replaced and rho delta v, and final formula 1 divided by 2 rho delta v, and changing velocity. Okay, and we know, and the work does, this force does work. We know, and the work F delta X, F1 multiplied by delta X1, but and F1 will replace and pressure, the first pressure multiplied by the second pressure. The second pressure, the first pressure multiplied by the first area and multiplied by delta x1 in here. But in here, and we replace area multiplied by delta x, we replace and delta v. And the second work, and the first work is positively, but and the second work is negatively, because and this is direction is opposite the first direction and the second direction, and this is we replaced, and for a final formula, and minus the second P2 multiplied by delta V. The total work done by this force and the changing pressure multiplied by delta V. We now, and the work energy theorem gives the total, W total equal potential energy, changing potential energy plus changing kinetic energy. But we know, and this is for total work done by this force in here. This is formula work energy theorem. We and the total work done by this force equal work energy theorem. And here, if we divide delta V in here, delta V, and delta V, we obtain and changing pressure equal changing in here, changing and rho g delta h, and in here changing and rho divided by 2 and square velocity changing 2 here, and the final formula in here, this is rho g h will be hydrostatic and pressure, and rho v square and dynamic the pressure. In here, this result and can be listed as P plus rho g y plus rho v square divided by 2 is a constant. And because and y1 equal y2, and changing pressure equal rho g h. Bernoulli's equation in here, and Bernoulli's equation, but and Bernoulli's is equation for the constant elevation, and P plus rho v square divided by 2 is a constant, and static pressure, dynamic pressure, and hydrostatic pressure. When and this is a feature show you construction in and pair, construction in a paper carrying a moving flow. Paper carrying in a moving flow, and the pressure is lower in the narrow section. Narrow section is lower, and the of the paper where is the fluid is moving faster. Even as the speed of fluid increases, the pressure drops. This is definition of Venturi effect. Maybe air flow around a wing foil, and the figure number A and figure number B. Figure number A show, and when the Y the horizontal, the flow is uniform, the pressure above the wing and is the same as the below it. And part number B and figure number B, when the one in the tilted, the pressure is greater at the bottom of one than the top of the wing creating lift. And here the final question, fluid fluid viscosity, and resistance. We now and fluid viscosity. Maybe we take in here one we take container, and the force is found. The force is found to be directional proportional to V, and area and inversely proportional to the plate separation and Z. But in here we know, and this is fluid, and in here this is the direction of the velocity, and one segment on the tube, and L, and this is length of the paper, and radius R, and the viscosity of the fluid we know. But in the coefficient of viscosity, this is eta, and the proportional to the constant is the coefficient of the viscosity eta, and here for the force found direction of the velocity and area, and the plate separation Z, and coefficient in here eta is the coefficient of viscosity for different element. Coefficient of viscosities are different, and this is tag, and we take, and here as it is the figure, and two plates. In here this is viscous fluid between two plates of equal to area with this viscosity between them. When the upper plate is moved related to the lower one, each layer of fluid exerts a drag force on layer. Is the force needed to pull the upper plate is directly proportional to velocity, and area, and here inversely proportional to the Z, the separation between the plates and Z in here. Okay, and we now and coefficient of viscosity for various fluid is different. Various fluid we know, and maybe water, maybe and blood, engine oil, and glycerin, air, etc. And this is temperature. And with a coefficient, viscosity coefficient. We know the system international unit of the viscosity, Pascal multiplied by second, in here millipascal multiplied by second, but our millipascal replace to Pascal multiplied by second. And we know we two type of the fluid, turbulence and laminar, and here, but and we know of turbulence or laminar to find Reynolds number. When the flow velocity of a fluid becomes, and laminar flow breaks down and turbulence sets in, the critical velocity above which flow through the tube is turbulent dependence on the density. Turbulence depends on the density and viscosity of the fluid, and of the radius on the tube. The flow of a fluid can be characterized by dimensionless number called the Reynolds number. In here, this is a formula of the Reynolds number, 2R rho V and divided by eta. R is the radius on the tube, rho and density of the fluid, and V in here, this is velocity of the fluid. This is where and average velocity of the fluid. Average velocity of the fluid. Experiments have shown and fluid flow will be laminar when if Reynolds number is less than about 2000, or turbulent the greater than 3000. Between these values, the flow is unstable and may change from one type to other in here. Laminar and less than about 2000, and the turbulent is the greater than 3000 in here. And here this is a turbulent motion of air, show around a vibrating cylinder, in a wide tunnel in the called vortex shading. The cylinder was oscillating normal to oncoming flow of air in the vortex were shed periodically in unison with the oscillation. Okay, and the cylinder was oscillating normal to oncoming flow of air and the voltage was shed periodically. In here, the Reynolds number was 200. The sheet minute aerosol particles was introduced into a wide channel upstream of the cylinder to make the flow pattern visible. Thank you for attention.